In this video, we shall see some of the exercise problems of chapter 7 of Fundamentals of Microelectronics by Razavi. Let us see problem number 7.1. Okay, in this chapter, some of the assumed quantities are given over here. Mu and Cox of NMOS is taken as 200 microampere per volt square. Similarly, for PMOS it is 100. VTH for NMOS is 400 microampere, 400 millivolt. And for PMOS it is minus 0.4 volt. Now we shall see what is 7.1 problem is. Here in figure 7.39 we are asked to determine the maximum allowable value of W by L if M1 must remain in saturation condition. So for this now you can see, since gate is tied to VDD through 50 kilo ohm resistance and the drain is connected to VDD through 1k resistance, now we are asked to find what is the maximum value of W by L so that this remains in saturation condition. Now we know that for MOSFET to remain in saturation condition, the VDS should be uh, at least equal to VGS minus VTH. Now what is VGS now? Now as we can see, now since gate is tied to VDD here and there is no drop across this 50 kilo ohm resistance, the entire 1.8 volts will come out here. So VGS happens to be 1.8. So VDS sat is now given by VGS minus VTH. Now it is 1.8 minus 0.4 happens to be 1.4 volt. Now for MOSFET to remain in saturation condition, the VDS of this M1 should be at least equal to 1.4 volt. So since we know what is VDS sat, we can actually find what is ID that should flow through so as to keep this MOSFET in a saturation condition. Now as we know that VDD, writing the KVL for the outer loop, VDD is equal to ID into RD plus VDS. Now this is the equation what we have. So this is ID into RD plus VDS that is equal to VT. So from this we can actually estimate the value of drain current that will flow through the MOSFET when the MOSFET is in at the verge of saturation condition, because VDS at we have taken it as 1.4 volt. So then the drain current comes out to be 0.4 millivolt. Substituting that ID is equal to 0.4 millivolt in the ID expression for saturation. So we know what is mu and Cox. We don't know what is W bell, which is to be found out now. VGS minus VTH we know. So upon substituting all these things, the value of W bell, of course, you can certainly use that alpha A version of your calculator. You can equate this 0.4 milliampere alpha equals, and this is 200 by 2, 200 micro by 2, and alpha A for this unknown quantity, and 1.4 whole square. If you do the shift solve twice, so the value of W will be directly coming as 2.04. So the maximum allowable value of W bell for this MOSFET to remain in saturation condition in this circuit is 2.04. So this way we can actually utilize the concept that what we know about the MOSFET to remain saturation is nothing but VGS minus VTH, and the drain current under saturation condition is given by mu and Cox W by L VGS minus VTH whole square. So using these equations we can actually find out what is W by L. See the second problem, 7.2. We wish to design a circuit in 7.40 for the drain current of 1 milliampere. And W by L, if W by L is equal to 20 by 0.18, compute the value of R1 R2 such that the input impedance is at least 20 kilo ohms. So please note that the input impedance should be at least 20 kilo ohm. Now these are some conditions given. So current should be 1 milliampere if W by L is so and so. Now this is a equation this is a circuit diagram what we have. So we are asked to estimate R1 R2 such that the input impedance of the circuit is at least 20 kilo ohms. Now from the available data, we can actually estimate the VGS that is required to have a current of 1 milliampere, which is specified over here, to flow through that with W by L as 20 by 0.18. So using the equation of ID is equal to mu n Cox by 2 into W by L VGS minus VTH whole square. Here we know everything except VGS minus VTH. So from which you can get the value of VGS, which is equal to VTH plus under root of 2ID by. So this is actually derived from this equation. So VGS comes out to be 700 millivolt. So this is the voltage at this point with respect to ground. So we can actually write the expression for VGS as also equal to R2 multiplied by VDD by R1 plus R2, that is using potential divider equation. So, and it is also said that the input impedance, which happens to be the parallel combination of R1 and R2, should be equal to 20 kilo ohm. Now, so let us assume that now, since VGS is less than half of VDD, so since this voltage is less than half of VDD, whatever resistance you assume R2, that will going to dominate the entire input impedance, because R2 will going to be lesser than R1, because we want to have a voltage less than half of this 1.8. So let us ensure that let the value of R2 to be twice of the required what input impedance, which is 20 kilo ohm. So that's why we are assuming this as 40 kilo ohm, so that R1 parallel R2 is minimum of 20k. Now we know that when this is 40k, and this has to be more than 40k, because you want to have a voltage less than half of your VDD here. Now assuming this as 40k, and substituting this voltage as 0.7, and we can actually estimate the value of R1, so which comes out to be 62.8 kilo ohms, and R2 is equal to 40 kilo ohms. And if you actually find out what is the R in, so it comes out to 24.4 kilo ohms, which is certainly more than 20k. Now the point here is, so since the input impedance asked is at least 20 kilo ohm, so we are actually finding out what is the voltage that is required here. Now since it is required to have 0.7 to have a current of 1 milliampere with W bell as 20 by 0.18, now we actually estimated that the voltage here should be 700 millivolt. For voltage to be here as 700 millivolt, now since we know that this 700 millivolt is obtained from this VDD, so this voltage is certainly less than half of this. If it was exactly half, then R1 is equal to R2. Now since it is less than half, the value of R2 should be less than R1. Now since R2 is less than R1, now when we actually find out the input impedance is actually the R1 parallel R2. If you choose this to be a lower value, then the overall combination will be lesser than this R2. So we have ensured that since R2 is dominating one, so we are assuming the value of R2 to be almost twice of your required input impedance. So that's why we assumed it to be 40k. Assuming this is 40k, to get a 0.7, R1 is found out to be 62.8. By having this 40k, that is 62.8 kilo ohms, so we are getting input impedance of 24.4, which is certainly more than 20 kilo ohms. Suppose by mistake, if you take this as 30 kilo ohm, if you actually find out the input impedance of, first R2 and then find out the input impedance, the input impedance may come less than 20 kilo ohms. So that's why in order to have an input impedance more than 20k, and since the voltage here is less than half of VDD, we assume this to be more than, okay, almost twice of the required input impedance. Even if you assume this as 50 kilo ohms, it's fine. Then the input impedance is more than 20 kilo ohms, but we should not assume lower than the input impedance required, which is 20 kilo ohms. Now let us see the third problem, that is 7 point. I hope this is the third problem. Now this is the third one. Now in the third one, so considering the circuit 7.41, which is over here, we are asked to calculate the maximum value of transconductance of M1 that can provide the MOSFET without going into saturation region. Here we are asked to find the transconductance. Now the VGS is not directly given here, because this is directly connected to the drain through 10 kilo ohm resistance. The VGS is 1.8 Now Vg is 1.8. Now this is what is we are having. The voltage at this point is 1.8, which is actually VGS plus ID into RS. So this is what is ID into RS plus VGS is 1.8, and threshold voltage is 0.4 volts. And GM, we know that it is 2ID by GM, 2ID by VGS minus VTH. So, and we know the expression for VGS as 1.8 minus course. So this is a VGS which is given over here. So here we have ID into this is ID into RS plus VGS happens to be VDD, because the current drop here is the voltage drop over here is 0, because there is no current going to the gate of the circuit. Now since we know that here VGS is equal to 1.8 minus ID into RS, and we are substituting here. So what is this, writing the KVL to the outer loop, VDD is equal to ID that is flowing through this 1K resistance as well as this 100 ohm, that is ID into 1K plus 100 ohm plus VDS sat. So the MOSFET, the minimum voltage for MOSFET to remain in saturation condition, which is VDS sat. But what is VDS sat? VDS sat is nothing but VGS minus VTH. But what is VGS? VGS is actually 1.8 minus this, what is 1.8 minus ID into RS. That's what is specified here. That's what is written over here. So VDS sat we know. So we can ultimately get the expression for VDD as equal to, this is ID into 1.1K plus VDS sat is substituted by this expression, and upon solving this, so we'll get the current of ID as 0.4 milliampere. Substituting this current of 400 microampere onto the equation of your ID, so we'll get the W bell as 2.41. So ID is W bell is given by 2 ID by mu n C ox VGS minus VTH whole square. This is actually the expression for the drain current in saturation condition, rewritten to find out the value of W bell. So once W bell is given, so we can actually find out what is GM. So since you know what is GM, so GM is equal to 2ID by VGS minus VTH. So ID we know, what is VGS minus VTH we know. So upon finding the values of ID and VGS minus VTH, the GM comes out to be 1 over 1700 ohm inverse, which happens to be 5.88 into 10 to minus 4 ohm inverse. Now this way we can actually find the transconductance of a circuit in this particular circuit, so without the values being directly given over here. So using this original equation of GM is equal to 2ID by VGS minus VTH, we can able to get this expression. We can also get the value of GM using another equation, that is under root of 2ID mu n C ox into W bell. So where you can use this W bell which is obtained here, and you know what is ID and you know what is mu n C ox, you can also get the value of GM using that equation also. So let us see the next problem. So in this problem we are asked to calculate the minimum allowable W bell if MOSFET M1 has to remain in saturation, and we are also asked to find what is R1 R2 if the input impedance must be at least 20 kilo ohms. Of course, now you can see first problem is we are supposed to find what is W bell of the M1 to keep it in saturation condition. So now we know that since the drain current is not directly given, but it is given that the voltage drop of 200 millivolt across RS. Now this is 200 millivolt across RS. Now this RS is given as 100 ohm. The drop is given as 200 millivolt. So naturally ID happens to be 2 milliamperes. So knowing the value of ID to be 2 milliampere, you know what is mu n C ox. We can actually find out what is VGS minus VTH. Now we know what is VDD now. So VDD is equal to ID into RD. So this is what is ID into RD plus VDS plus ID into RS. So that is writing the KVL to the outer loop. So now VDS is equal to VDD minus ID into RD. So VDS comes out to be 0.6 millivolts. So this is 0.6 millivolt, which is the voltage across the drain. Because we know VDS at a 0.6 millivolt, we can actually find out what is VGS from this expression, because VGS minus VTH is equal to VDS at. So VGS comes out to be 1 volt. So from this value of VGS we can actually obtain the value